Good morning, everyone. Today I will present our work, Streaming Video Crime Anticipation with Spatio-Temporal Causal Reasoning. The core problem we study is how to anticipate future crimes from streaming surveillance videos before the crime actually occurs, instead of only recognizing an abnormal event after it has happened. Our goal is to identify early visual and causal cues that may lead to our future criminal events. The motivation is that crime anticipation is fundamentally different from conventional anomaly detection. Anomaly detection usually asks whether the current video clips is abnormal. In contrast, crime anticipation tasks asks harder questions. Based on what has happened so far, can we predict whether a crime is likely to happen in the near future? This requires reasoning about how entities and interactions evolve over time. For example, in a robbery scenario, the robber may suddenly accelerate towards the victim, or the distance between the weapons and the victim may gradually decrease. These are not isolated visual patterns, they are spatio-temporal causal cues. Existing video understanding models often lack explicit mechanism to model such causal relationships. To address the data limitation, we construct the spatio-temporal causal reasoning crime dataset, called STCRC. The key idea is to convert raw surveillance videos into structured causal reasoning data. Specifically, we annotate temporal events, entities, spatial relationships, and organize them into 5 hierarchical reasoning tasks. Task 1 predicts the intermediate next events. Task 2 predicts the future spatial layouts of entities. Task 3 recovers the causal temporal order of events, and Task 4 selects true causal events from distractors. Task 5 identifies which entities cause the target events. Together, these tasks teach the model not only what has happened, but also how events, spatial relationships, and entity contribute to the future crimes. Our framework contains 5 major components. First, the annotation model extracts the event entities, depth information, checking IDs, and motion features from streaming frames. Second, the spatial-temporal causal hypergraph, called STCH, converts these implicit entity dynamics into explicit graph structures. In STCH, each entity is represented as a node with positions, velocity, acceleration, trajectory, morphology, semantic category, and temporal metadata. The model then detects 2 types of causal events. The first is causal cascade effects, which captures how a motion change in one entity may trigger responses in nearby entities. The second is group evolution, which captures aggregation or separation among multiple entities. Then the hypergraph is translated into graph tokens and inserted into the VOM. A memory bank is also used to return long-stream context. Finally, the model is jointly trained on spatial-temporal causal reasoning tasks and downstream anticipation tasks, including detection, classification, and time-to-crime prediction. We evaluate our method on UCF crime and XD violence and compare it with the traditional deep learning method, offline VLNs and streaming VLNs. The results show that our method achieves the best overall performance. Finally, we evaluate the efficiency and robustness of our model. The latency results show that our method achieves a better prediction quality while maintaining a response delay comparable to efficient streaming baselines. This is because the graph information is injected as token into the VOM embedding space. Instead of introducing a heavy sequential model, we also test robustness under detection noise, depth noise, and checking noise. The performance degrades gradually rather than collapsing, which stress the model learns stable spatial temporal motion patterns instead of relying only on precise low-level perceptions. To conclude, our model contributes both a new causal reasoning dataset and a streaming hypergraph module. Together, they enable VLMs to reason about entity interactions, temporal dependencies, and causal precursors for real-time crime anticipations. Thank you very much for your listening. This is the overall of our work.